We toss numbers around every day, right? Like it's nothing. But I'm curious, have you ever, like, hit a wall? Like a real mathematical wall where the numbers just don't cooperate?
Oh, I know exactly what you mean.
Like, say you're trying to solve this equation. X squared plus 1 equals 0.
Yeah.
Suddenly, all those familiar numbers, positive, negative fractions, they all sort of give up.
Right.
It's like you're asking them to do something they just can't. You can't square any real number, no matter how hard you try, and get a negative result.
Absolutely. You're hitting those limitations of the real number system. It's a genuine head scratcher.
It is. It's a real puzzle. And that's actually where we're going to kick things off today. Because, mathematicians, they don't back down from a good puzzle.
Never. That's what makes it so fun.
Yeah.
That seemingly simple equation, the one you mentioned,
Uh-huh.
was a huge driving force for pushing the boundaries of math.
It was.
Oh, yeah, it's a big deal. And the quest to solve it led to this really elegant concept, complex numbers. They're like, think of it as an upgrade to our regular number system, And they're specifically designed to handle those tricky equations, like the x squared plus 1 equals 0, the ones that real numbers just can't handle.
So they're coming to the rescue.
Exactly. They come in and save the day. And they take this form, it's a plus IB, where it's this new element, kind of a rock star. It's the square root of -1.
So today, we're taking a deep dive into complex numbers. And we've got some great material to guide us. We're looking at excerpts from a chapter that really digs into these numbers, along with quadratic equations.
Sounds good.
So our mission today is to, break down the basics. What are these complex numbers all about? How do we work with them? Can we actually picture them? We want to get to the heart of it all to give everyone a solid understanding, without getting too lost in the weeds. We're going for clarity here.
Precisely. We want you, our listeners, to walk away feeling confident about what complex numbers are and why they're so important, especially in math.
So let's jump right in, shall we? Right to the beginning, the birth of this this mysterious square root of -1. It almost feels like a contradiction, right? Like, how can squaring anything, result in a negative number? It's like saying up is down.
I know. That's what's so cool about this. See, instead of trying to force I to fit into the rules of real numbers, mathematicians got creative. They took a leap. They said, okay, what if we just roll with this? What if we pretend or hypothesize that there's a number whose square really is -1?
Yeah.
And let's see where that takes us. That willingness to think outside the box, to play with seemingly impossible ideas, that's often what leads to huge breakthroughs in math.
It makes sense.
Like Gauss, the math whiz. You said it best.
Yeah.
Mathematics is the queen of sciences, and arithmetic is the queen of mathematics.
That's quite a statement.
It is. And, even something as basic as arithmetic can grow and change, to face new challenges.
It can evolve.
Exactly. It evolves. I bet W.R. Hamilton, another math giant, he'd totally agree on that,
Okay.
on how important this kind of exploration is.
So we've got this this imaginary unit, but a full-blown complex number, it's not just hanging out on its own, right?
Nope. It's a team effort. The standard way to write a complex number is a plus IB.
Okay.
A is the real part, the down-to-earth part. We write that as Resi sometimes.
Resi, got it.
And then B, that's the imaginary part, the one with the I attached. We write that as IZ. So it's this cool mix, a real number and an imaginary number working together.
Like a buddy cop movie.
Exactly.
Yeah.
Like if you see 2 plus I3, 2 is the real part, 3 is the imaginary part, easy peasy.
Okay, and if we have -1 plus 3i?
Real part's -1, imaginary part's 3. See, not so bad.
And what about those fractions, like 1/4 minus I 11/5?
Same deal. Real part's 1/4, and the imaginary part's -11/5. It's all about keeping those parts straight.
So how do we know when two complex numbers are actually equal? Like, what's the rule?
Good question. Okay, so let's say we have two complex numbers. Call them Z1 equals A plus IB and Z2 equals C plus ID. They're only equal if both their real parts match up. So A equals C, and their imaginary parts are the same. B equals D. It's like a double check. Both have to be true at the same time.
I see. And our source gives us a nice example. If we have the equation 4x plus I times the quantity 3x minus y, and that equals 3 plus I times -6, and we know that x and y are real numbers, we can actually solve for x and y.
We can. How?
By matching up those real and imaginary parts like you said. So 4x has to equal 3, which means x is 3/4. And the imaginary part, 3x minus y, has to equal -6.
I'm following.
If we plug in that 3/4 for x, we get 3 times 3/4 minus y equals -6, which is 9/4 minus y equals -6. And if we solve for y, we get 33/4. So it's like we're taking this one complex equation and splitting it into two real number equations that we can solve.
Exactly. It's a clever way to take something new, complex numbers, and turn it into something familiar. Real number equations. It's a neat trick. Now that we know what a complex number is, let's dive into how we can do math with them.
Sounds good to me. Where do we start?
How about addition? Nice and easy. Let's take two complex numbers, same as before. z1 equals a plus ib, and z2 equals c plus id. How do we find their sum?
Okay, ready.
It's pretty intuitive. You just add up the real parts, then you add up the imaginary parts separately. So z1 plus z2 equals the quantity a plus c plus I times the quantity b plus d. And what you end up with, you guessed it, another complex number.
It's like they just want to stick together.
They do. Okay, here's a real example. 2 plus I3 added to -6 plus I5.
Yeah.
That gives us 2 minus 6 plus I times 3 plus 5, which simplifies to -4 plus I8.
So it's kind of like combining those like terms.
So exactly, you've got it.
Right.
And just like with regular numbers, addition with complex numbers follows some rules, some important properties.
Lay them on me.
Okay, first up, it's closed. Meaning, when you add two complex numbers, what do you get? Another complex number.
They're sticking together.
Always. Then there's commutative. The order doesn't matter in z1 plus z2. It's the same as z2 plus z1. Swap them around, no problem.
Okay, that makes sense.
Third, we've got associative. That's about grouping. So the quantity z1 plus z2, then plus z3, it's the same as z1 plus the quantity z2 plus z3. Group them however you like.
So far, so good.
Now we've also got our additive identity.
Additive identity.
That's just 0. You can also write it as 0 plus I0 if you like. It's the number that when you add it to any complex number, that complex number stays the same.
It's like the complex number doesn't even notice it's there.
Precisely. And last but not least, every complex number, z equals a plus ib, it has an additive inverse.
Which is?
Negative z, which is just negative a minus ib.
Yeah.
When you add a complex number and its additive inverse, you get, you guessed it, 0. Back to the identity. It's like they cancel each other out.
It's really cool how a lot of the rules we already know, they just carry over into this new complex world.
Isn't it? It's really quite elegant. It really does feel like a natural extension, doesn't it?
It does. So what about subtraction? How does that work with complex numbers?
Okay, well, subtraction actually relies on addition.
It does.
It does. To subtract z2 from z1, we just add the additive inverse of z2 to z1. So z1 minus z2 is really just z1 plus negative z2.
Oh, I see.
So if z2 is c plus id, then its additive inverse, negative z2, is just negative c minus id.
Okay.
So when you put it all together, z1 minus z2 becomes the quantity a minus c plus I times the quantity b minus d. Again, you're working with those real and imaginary parts separately.
So it's like parallel processing.
Exactly. Okay, here are a couple examples. 6 plus 3i minus the quantity 2 minus I. That becomes 6 plus 3i plus negative 2 plus I, which gives us 4 plus 4i.
Okay, I'm following so far.
Now let's flip it around. 2 minus I minus the quantity 6 plus 3i becomes 2 minus I plus negative 6 minus 3i, and that equals negative 4 minus 4i. So just like regular subtraction, order totally matters here.
Absolutely. No swapping things around willy-nilly.
Nope. You'll get a different answer.
All right, so we've covered addition and subtraction. What about multiplication? How does that work in the world of complex numbers?
This is where things get a little more interesting. We've got our z1, which is a plus ib, and z2, which is c plus id.
Right.
Their product, z1 times z2, is defined as this: the quantity ac minus bd plus I times the quantity add plus bc.
Okay, that's a bit more of a mouthful.
I know, right? But you can actually get this by using the distributive law, the one we all learned way back when. You expand the product of a plus ib times c plus id, and then the magic happens. Remember that I squared equals negative 1.
Right. The fundamental IFA fact.
Exactly. Let's try it out with an example. 3 plus I 5 times the quantity 2 plus I 6.
Okay, let's see this in action.
That expands to 3 times 2 plus 3 times I 6 plus I 5 times 2 plus I 5 times I 6.
I see. So that gives us 6 plus 18i plus a 10i plus 30i squared.
Right. And then we swap out that I squared with negative 1.
Which gives us 6 plus 28i minus 30.
And simplifies too.
Negative 24 plus I 28.
See? That formula, the quantity ac minus bd plus I times the quantity add plus bc, it pops right out.
I'm starting to see how all the pieces fit together. Does multiplication with complex numbers also follow those properties, like real number multiplication?
It sure does. It's also closed, meaning multiply two complex numbers, you get another complex number. No surprises there.
Sticking to their own kind.
They like their group. It's also commutative, so z1 times z2 is the same as z2 times z1. And associative, so grouping doesn't change the outcome.
Okay, that sounds familiar.
And just like before, we've got our multiplicative identity,
Which is?
1. Or you can write it as 1 plus I0 if you want to be fancy. Any complex number times 1, it's just itself.
Doesn't change a thing.
Exactly. And one more important property. Every complex number, except for 0, has a multiplicative inverse.
Like a reciprocal.
Yep, exactly like that. We write it as 1 over z, or z to the power of -1. And a number times its inverse, they multiply to give you, guess what?
1. Back to the identity.
You got it. And let's not forget the distributive law.
Right, that one's important.
It says z1 times the quantity z2 plus z3, that equals z1 times z2 plus z1 times z3. And it works the other way around too. It's just like distributing with real numbers.
So reassuring to know that those rules still apply.
I know, right? It makes venturing into this new territory a bit less daunting.
It really does. Okay, now division with complex numbers. It seems like that might be the trickiest one of the bunch.
You know, it can look a bit intimidating at first, but there's a handy trick that makes it much easier.
I'm all ears.
So to divide z1 by z2, where z2 is not 0 because we don't want it to divide by 0, that's always trouble.
Never a good idea.
We define it as z1 over z2 equals z1 times the quantity 1 over z2, which means we're multiplying z1 by the multiplicative inverse of z2.
Right, that reciprocal idea.
Precisely. So the formula for the multiplicative inverse of a non-zero complex number, z equals a plus ib, is this. Z to the -1 equals a divided by the quantity a squared plus b squared minus I times b divided by the quantity a squared plus b squared. It's a bit of a mouthful.
It is. Is there like a more practical way to actually do division?
Absolutely. This is where the complex conjugate comes into play.
Conjugate.
It's a fancy word for a simple idea. The conjugate of a plus ib is a minus ib. You just flip the sign of the imaginary part.
Okay, doesn't sound too bad.
It's not, and it's really powerful. What you do is you multiply both the top and bottom of your fraction by the conjugate of the denominator. This little trick makes the imaginary part in the denominator disappear, which simplifies things a lot.
Oh, I see. That's clever.
Like in this example, 6 plus 3i divided by 2 minus I. We multiply the top and bottom by the conjugate of the denominator, 2 plus I. So we get the quantity 6 plus 3i times 2 plus I, all divided by the quantity 2 minus I times 2 plus I. That gives us 12 plus 6i plus 6i plus 3i squared on top, and 4 minus I squared on the bottom.
Right, and remembering our fact, I squared is -1.
We get 12 plus 12i minus 3 on top, and 4 plus 1 on the bottom.
Which gives us 9 plus 12i over 5, or 9/5 plus I times 12/5. That is much tidier.
It is, right. It takes that division and transforms it into the standard a plus ib form.
Yeah.
And using the conjugate is usually the most efficient way to do complex division.
It's a great tool to have in your back pocket. So we've covered the basics, the fundamental operations. Now, what about those powers of I? You know, we started with I squared equals -1.
Right.
What happens when we raise I to higher powers? Does it just get crazier and crazier?
Actually, no. This is where it gets really neat. The powers of I, they form a pattern, a repeating cycle. We know I to the power of 1 is just I squared is -1. Then I cubed, that's I squared times I, which is -1 times I, or -I.
Okay.
And I to the 4th, that's I squared times I squared, which is -1 times -1, giving us 1.
So it's a loop.
It is a 4-step loop. I, -1, -I1, and then it starts all over again, like a merry-go-round of I's.
That is a surprisingly neat pattern. So how do we use this to figure out I raised to any power, like a really big power?
Easy peasy. For any integer k, we have these rules. I to the power of 4k equals 1. I to the power of 4k plus 1 equals I to the power of 4k plus 2 equals -1. And I to the power of 4k plus 3 equals -I.
Got it. So if we have I raised to some huge power, all we need to do is divide the exponent by 4, and the remainder tells us where in the cycle we land.
Exactly. Like, let's say you have I to the power of 100. 100 is divisible by 4, no remainder, so I to the power of 100 is the same as I to the power of 4 times 25, which equals 1. What about I to the power of 2023?
Okay, that's a big one.
If you divide 2023 by 4, you get a remainder of 3. So I to the power of 2023 is the same as I to the power of 4 times 5 over 5 plus 3, which is I cubed, or negative I. See,
Oh,
much easier than multiplying I by itself over 2,000 times.
that's a fantastic shortcut. Now, the source also mentions powers of 1 over I. What can we say about those?
Well, 1 over I, we can simplify that by multiplying both the top and bottom by negative I, which is the conjugate of I. We'll get into conjugates a bit more later.
Hmm.
So 1 times negative I divided by I times negative I, that's negative I, divided by negative I squared,
Which, substituting -1 for I squared.
becomes negative I divided by negative 1, which is negative I over 1, or simply negative I.
Oh, that's pretty straightforward. So 1 over I is just negative I.
And that means the powers of 1 over I, they're also going to follow a cyclical pattern, just like the powers of I.
Makes sense. Okay, let's go back to the beginning, to that square root of -1. We defined it as I, but what about finding the square roots of other negative real numbers?
Ah, good point. So if you have a positive real number, let's call it A, then the square root of negative A can be written as the square root of the quantity A times negative 1, which is the same as the square root of A times the square root of negative 1, or I times the square root of A.
So the square root of, say, -3 would be I times the square root of 3.
Exactly. And the square root of negative 9 would be I times the square root of 9, which simplifies to 3I. This is a simple way to handle those negative signs under the radical.
It is, but there's a little caveat mentioned here. The usual rule, the square root of a product is the product of the square roots. It doesn't always hold true when both numbers under the radical are negative. Why is that?
It's a trap, a common mistake. You might think that the square root of negative 1 times the square root of negative 1 is equal to the square root of the quantity negative 1 times negative 1, which would simplify to the square root of 1, or just 1.
Right, because -1 times -1 is +1.
Exactly. But here's the catch. We define the square root of negative 1 as I. So the square root of negative 1 times the square root of negative 1 is actually I times I, which is I squared, which we know is negative 1.
Oh, that makes sense. So the rule breaks down when both numbers are negative.
It does. The rule, it works fine when we're dealing with positive numbers. And even if one is positive and the other is negative, but those double negatives, they throw a wrench in the works because of how we've defined I.
Gotcha. It's like a special case. Now, what about algebraic identities? The source mentions that the familiar identity, the quantity z1 plus z2 all squared equals z1 squared plus 2 times z1 times z2 plus z2 squared, it actually holds true for complex numbers too.
It does. The proof of that identity relies on those distributive and commutative laws we talked about earlier. Since those laws work for complex numbers, many of the algebraic identities we use with real numbers, they just naturally extend to complex numbers.
It's like the rules are the same no matter what kind of number we're dealing with.
Precisely. And the source also lists a bunch of other identities that are true for complex numbers too, like the quantity z1 minus z2 all squared.
Right, and then there's the quantity z1 plus z2 cubed, and the quantity z1 minus z2 cubed, and also that difference of squares, z1 squared minus z2 squared equals the quantity z1 minus z2 times the quantity z1 plus z2. All these familiar tools, they still work.
They do. It's good to know that all those tools from the real number world are still useful here.
Absolutely. And the source then gives some examples of, actually working with complex numbers, expressing them in that standard A plus IB form.
Right. Like those examples, they're really helpful. They show us how these rules work in practice.
Like those problems where you simplify expressions with powers of I.
Exactly, like that I to the power of negative 35 plus I to the power of negative 48. That one forces you to use that cyclical pattern of I.
And then there are those where you expand powers of complex binomials, like the quantity 5 minus 3i all cubed.
Ah, yes. That one makes you use the binomial theorem carefully, always remembering that I squared is negative 1 and I cubed is negative I. And then there are those where you simplify products and sums of complex numbers, like 3 minus I times 2 plus I, plus the quantity negative 2 minus 3I times 1 minus I. It's a good workout for those basic rules of addition and multiplication.
I'm starting to feel like a complex number expert.
Practice makes perfect.
Mm.
Okay, now let's move on to two more important concepts. Modulus and conjugate.
Modulus and conjugate.
They're like key tools for working with complex numbers.
All right, I'm ready.
So for a complex number, z equals a plus ib. The modulus, we write that as the absolute value of z. It's a non-negative real number. It's defined as the square root of the quantity a squared plus b squared, Geometrically, and we'll see this in a bit, it represents the distance of the complex number from the origin on the complex plane.
Okay.
Think of it as like the size or magnitude of the complex number. Then there's the conjugate of z. It's written as z with a bar over it. It's a minus IB. You just flip the sign of the imaginary part.
So it's like its mirror image.
Exactly. And this little flip, it's got some really cool consequences, especially when we're doing division.
So let's look at some examples. The modulus of 3 plus I would be the square root of 3 squared plus 1 squared, which is the square root of 10.
Right.
The modulus of 2 minus 5i is the square root of 2 squared plus negative 5 squared, which is the square root of 29.
Okay.
And look at this. The modulus of 2 minus 5i is the square root of 29, and the modulus of negative 2 plus 5i. It's also the square root of 29.
Get at it.
Then we've got the modulus of 3i, which is the same as 0 plus 3i. That's the square root of 0 squared plus 3 squared, which is just 3. And the modulus of negative 3 minus 5i is the square root of negative 3 squared plus negative 5 squared, which is the square root of 34. So the modulus, it's always a positive real number, or 0, just like the definition says.
It is. And what about the conjugates?
Okay, the conjugate of 3 plus I is 3 minus I.
Easy enough.
The conjugate of 2 minus 5i is 2 plus 5i. The conjugate of 3i, or 0 plus 3i, is negative 3i, or 0 minus 3i. The conjugate of negative 2 plus 5i is negative 3 minus 5i, and the conjugate of negative 3 minus 5i is negative 3 plus 5i. So it really is just flipping that sign in the middle.
It is. Now, here's what makes the modulus and the conjugate so cool. They're related in a special way. The multiplicative inverse of a non-zero complex number z can be expressed as the conjugate of z, divided by the modulus of z squared.
So the inverse is linked to both the conjugate and the modulus.
It is. And this also means that z times its conjugate equals the modulus of z squared. This is a super useful identity when you're simplifying expressions or doing division.
It's like a secret weapon.
It kind of is.
Yeah.
Okay, the source also mentions some important properties of conjugates.
Right.
For any two complex numbers, z1 and z2, the conjugate of their product, it's just the product of their conjugate.
Okay, so you just take the conjugate of each one separately, then multiply.
Exactly. And it works for division, too. The conjugate of a quotient is the quotient of the conjugates.
As long as we're not dividing by 0.
Of course, always got to watch out for that 0 in the denominator. Now, the conjugate of a sum or difference of two complex numbers, it's the sum or difference of their conjugates.
So same deal. Conjugate each one separately, then add or subtract.
You got it.
Yeah.
And last one, if you've got a real number, let's call it k, and you multiply it by a complex number z, the conjugate of that product is just k times the conjugate of z. So those real numbers, they just hang out, no need to change their signs.
It's good to know that real numbers still play by the rule.
They do. They're good like that.
So we have an example here about finding the multiplicative inverse of 2 minus 3i using both the formula and the conjugate method.
Let's do it.
Okay, using the formula, we get 2 divided by the quantity 2 squared plus negative 3 squared minus I times negative 3 divided by the quantity 2 squared plus negative 3 squared.
Right. And simplifying that, what do we get?
2/13 plus I times 3/13.
Okay, now let's try the conjugate method.
The conjugate of 2 minus 3i is 2 plus 3i, and the modulus squared is 2 squared plus negative 3 squared, which is 13. So the inverse is the quantity 2 plus 3i divided by 13.
Which is?
2/13 plus I times 3/13. The same answer.
It works both ways.
Yeah.
And that should give you confidence that you're understanding these concepts correctly.
It does. And we have another example here about expressing the quantity 5 plus 2i divided by the quantity 1 minus 2i in that standard a plus ib form.
Right. And for that one, we use the conjugate of the denominator again.
Which gives us 1 plus 2i as the final answer. And then there's simplifying I to the power of negative 35.
Ah, that one uses the cyclical property we talked about earlier.
And it simplifies to?
Negative I, or 0 minus I, if you want to be super precise.
So these examples, they really show how useful the modulus and conjugate are for working with complex numbers.
They're like essential tools in our complex number toolbox. Okay, you ready to shift gears a bit?
Always.
Great, because now we're going to get visual. Instead of just thinking about complex numbers as these pairs of real numbers, we can actually see them on a plane.
A plane.
It's called the Argand plane, sometimes the complex plane. It's this two-dimensional space where the horizontal axis is the real axis. That's where the real part lives.
Makes sense.
And the vertical axis is the imaginary axis, where the imaginary part hangs out. Each complex number, z equals x plus iy. It corresponds to a point, x comma y, on this plane. So the real part, it tells you how far to go left or right, and the imaginary part tells you how far to go up or down.
It's like a map for complex numbers, and our source includes a figure that shows how different complex numbers are plotted as points on this plane.
Oh yeah, that's super helpful.
It's really cool to see. You've got 2 plus 4i, negative 2 plus 3i, 0 plus I, 2 plus 0i, negative 5 minus 2i, 1 minus 2i, all laid out like little landmarks in this complex landscape.
It makes it so much easier to grasp what a complex number is when you can actually see it, right?
Absolutely.
Now here where it gets even cooler. Remember the modulus, the absolute value of z, the square root of the quantity x squared plus y squared. Well, if you look at it on the Argand plane, it's just the distance from that point x comma y that represents the complex number to the origin 0 comma 0.
So the modulus is telling us how far the complex number is from 0.
Exactly. It's like a measuring stick in this complex world.
I like it. And what about the conjugate? Where does that fit into this visual representation?
The conjugate, z, with a bar over it, which is x minus I weight c, it's represented by the point x comma negative y.
Yeah.
And if you look at the Argand plane, it's the mirror image of the original complex number z.
So if you drew a line straight down from z to the real axis, the conjugate would be the same distance away, but on the other side of that line.
Precisely. It's
Correct.
reflected across the real axis. And this visual relationship, it really reinforces that algebraic connection between a complex number and its conjugate. They're linked both visually and algebraically.
That's really elegant. Now, the source also mentions the polar form of a complex number.